Presentations here that I'm going to go through, and then at the end I'll open it up for any kind of technical questions. We saw a little bit about this before, but part of this thing is that guys understand is how much engineering we do. And I don't know why you get this comment that says, I don't know what Buell or EBR is doing because they're doing some dumb stuff. And, any real engineer would know you don't do it that way. Well, that's absolutely correct. Because there's a tremendous amount of engineering that goes into it, and it's just that combination of being a little bit innovative. So we basically did FEA and optimization on every part on the bike. That's why it's so dang light. You start with a bike with a V-twin motor, they're heavy. They're heavier, a lot heavier than four-cylinder. And yet we're next to the lightest bike in the class, lighter than all the four-cylinder bikes. It takes a lot of work because the teams who are working on those bikes are good from the other factories. And it takes a ton of work to do it. So we did a lot of simulation, whether it's horsepower simulation, whether it's airflow, whether it be CFD work, FEA work, a ton of testing in a lab or road testing with all kinds of data collection equipment. So it's either we have an MTS machine that's run by a computer that can put cyclical hydraulic loads into a chassis or a vehicle, or as much as we want to, with any kind of a computer profile. So you can go out and map the profile of what the loads are in a chassis using strain gauges, and then come back and duplicate that in the lab, and then run that without having to ride the bike and get it to work done in a really short period of time. And then, of course, we do racetrack testing, and it's not just racetrack testing for racetrack time. We do racetrack testing for production bikes, because with fast riders, a high-level rider, because they do stuff that's crazy. They damage stuff you wouldn't believe, just because they ride so violently. And then we did a lot of testing at the time we were using proving grounds down in Arizona for mileage accumulation. And then I have to sit here sideways, because I like to walk around more than this. Talk about the things we did with the design on the bike, because we have a unique look, and we wanted to have a unique kind of American look on our super bike, something different. And it started with me, I wanted the idea of, instead of, okay, everybody's done the anthropomorphic thing with that, with eyeballs this way and this way. So it's not an animal, it's a vehicle. And I just wanted to have one long, kind of the idea of a diesel locomotive or a fighter plane. There's one thin line, down the middle of the cockpit, and one headlight. So, and into that, then we integrated LEDs. I know that's when we came to South 14. We were the first company to have. I don't know where the other guys are, but it's full LED headlight and tail light. And the LED headlight is absolute to the max limit of what you're allowed to have for lawn. It is bright. Guys have ridden in our so that's like at night. It's a potent headlight. This thing with what we did with the tail light floated out there. The idea behind that is we just kind of wanted to make it a race bike, and it just happens to have a tail light on it. We did it with one package, so with 3 screws, you can unscrew it at the track and take it off, and now you look like a MotoGP bike, And that took a lot of work to build that, because all those pieces have to be on there and hung on there, and you want it to look light enough, but it has to be heavy enough to handle going over the bumps and everything with a license plate weight on it.
Okay, it's your chair, right?
That looks like a bar stool. I should be comfortable here. And just a whole lot of little details is, I really like the flow of certain of vehicles where everything has kind of one theme, whether it's a 53 Studebaker or an Excade. There's just certain looks that I like. Some designs get really busy with a lot of, like, look at this cool piece, and look at this little neat piece, but when you back away from them, it's a little chaotic. And I like when you back away from a vehicle that's like, you know what it is right away. And that's kind of what, we did there. Just a quick thing on the cockpit, again, it's a color
all color LED system. And this, it's all designed to a vanishing point. If you look at it, you see it. I mean, it's got this one, you know, I think, you know, your design doesn't look like the other bikes. It's weird. I think the other bikes are weird. This looks like what it's supposed to look like. It just has that flow. I think it's gorgeous. It's funny. It's because some people have done it. A lot of the car guys at Cadillac design, oh, they said your bike is absolutely gorgeous. But they're kind of edgy design. Okay, enough about that. Talk a little about this engine, powertrain, and again, I'm going to kind of run through this stuff, and at the end, if you guys want to ask more questions, we will. So I'll try to go through this kind of fast, but just tell a little story about this. This engine was conceived, built, and tested now in America. It's an engine, the core original engine was done between Buell and Rotax back in the day, but it's a unique engine. It was not a Rotax engine. It didn't share any parts of theirs. It was unique, and when Buell was shut down, Rotax wound up inheriting the engine from Buell Harley, and they sold it to me because they said it doesn't work. This doesn't match any of our other engines. It's your engine, and we can't use it because it's all of our stuff is modular. This engine is, you know, totally your design. And some of the stuff we did in it. Now, the core engine is. I can talk about that more later, but you guys may know about it. It's a double overcam 4-valve revolver that makes a whole lot of horsepower. But there's some innovations in that you probably don't know about. One of them is this Csi Induction System. What we have there is swirl is well known in the 2-valve world, and that was one of the first things they do to clean up 2-valve motors, and Harley has to work on that a lot, any of those motors. And they've done it in the 4-valve world with deflector pistons or skewing the port. But a typical high-performance 4-valve motor, everything is symmetrical, flow comes straight in, and they have what's called tumble. Tumble is not as good for emissions, not as good for clean burn as swirl. So what we did is we kick open one intake valve just slightly before the other. And that initiates a swirl out the port. Then we have a bypass port in the intake manifold on one side, on the same side where that valve kicks open. And that's controlled by the ECU. And it adds airflow to that mixture, depending on what RPM the load is, to increase and decrease that swirl. We also have quarter wave tuners in the engine, in the exhaust system. There's actually two of them. There's a short wave tuner that's down in here, and this long wave tuner. I'm not loud enough, am I?
No, you're not. But on that intake valve, can you go back on that percentage of the EPA emissions where we're at?
Yeah, I come to that in a minute. I should have put them on a sequence. I will tell you, because I'll talk to you a little more about what that swirl did to us. I'm sorry. If this is a little out of phase. This is a long wave tuner. So you look at those two pipes going up there. Actually, exhaust only is going through one of them. The other one is a capped off quarter wave tuner that puts a big boost into the mid-range and cuts noise at the same time. And we'll show you what the power band looks like, which is partly because of that. One of the things, you know, the reason we have the fuel in the frame is that we have a gigantic airbox, because in order to get maximum power out of a big engine like this, you need a huge still airbox. And that original concept, I built a prototype of that frame in '88 for the original Harley VR project that I got thrown off of. But that's when that dates back to, because when I was designing the original VR engine concept, which I made it out of 2 BDG cylinder head, which is a 4-cylinder 2-liter Cosworth engine, a BDG. So when Harley at that time wanted to go road racing, and they didn't know what they were going to race, so I came back with a concept. You ought to make, the rule is you only have to make 50 of a 1,000cc bike. Don't make something out of your XR. Build something fresh. We only have to make 50. Let's basically take half of a BDG, make it into a V-twin, make it a 60-degree motor, and do that. But when I talk to the guys at Cosworth, how do you get so much power out of naturally aspirated engine? They said, well, one is you need ram air, but that's not enough. They said you need ram air and you need a huge still air box. And it has to be sized by the size of each cylinder that's taking a go. And they told me the size, which was 20 plus liters. And I went, that's a gas tank. So that's where fuel and frame started. But another thing that's not known on these bikes is the charcoal canister. So we were looking at that, as you know, those, if you go online, you can find anywhere how to take the charcoal, hideous charcoal canister off of your Ducati Monster or your Aprilia. They this tube thing grafted on the side with hoses hanging out, you know, and it's how do you do that? Well, I kind of think that I like to go fast. I like, there's certain regulations I don't like, but I do want to be green. I don't want to pollute. And if the rule, I say, if I can go really, really fast without polluting, that's fine. So this is part of it. So every one of those bikes, not California ones, they all have charcoal canister, even though it's not needed in 49 states. Because I put it inside the airbox. So it's molded in, that's there. And the other thing is, right near the airbox is right where the fuel system is, so that's where the vapors are coming out. So I don't have to run hoses all over the motorcycle, so if they go, they're about this long and they're into the airbox. And I then take the fuel, when the excess fuel accumulates, it gets pulled out to a port, but I pull it out with the ECM and blend it with the fuel from the tank. So I don't ever hit a glop of fuel burn. The results of the way the engine is tuned is a couple things. We make 185 crank force, which is usually on a Dynajet 162 or so at the rear wheel. 102 foot-pounds of torque. But look at the torque curve. It's not a curve. It's flat. We've got 75% of the max torque over 7,000 RPM. There's no other engine out there like that. That's one of the reasons this engine feels so flat. And sometimes it's deceivingly feels slower than it is, because you never feel a jerk in it. It just goes, whoop, whoop. And I had some guy put up a post said, I rode one of those things the other day and the speedometer is bullshit because it wasn't fast and it was saying it was going 120 miles an hour. There's no way. Whatever. But that's bullshit. And you know, that's what I was trying to get with this engine. Some of the neat qualities that the old Buell air-cooled Buells had. It was a really nice fat power band. It ended way too soon. And so I wanted to keep that and just carry it on out. So you can ride these things around all day, board up that 7,000 RPM. They're fast, powerful, running things. And then you go to 11 and it's and before I get to the emissions thing that Chris was reminding me about, this is what we were shooting for. This is another competitive import twin superbike, a good one, with good horsepower. Makes about 4.5 more horsepower than us at peak. Look where you ride. We got over 20 horsepower. The area under the curve is staggeringly different. And when you read the magazine road test, you think, oh, you know, they fell short. No, we didn't. Ride the bikes. That's not inconsequential. This is a great company that built that bike that makes 4 more horsepower than us, but a whole lot less horsepower than us. And we didn't luck into it. We did it by engineering. We did it with innovative engineering. The other thing is we do our own, not only as mechanical parts, like this is talking about with what we did in the combustion chamber, but we also have our own engine management system. We don't use Delphi, we don't use Magnetic Morelli, we don't use Bosch. We use our own. That's proprietary. We work with a company in Indiana that developed it. And our dash is integrated with it, and that's done by a company in Wisconsin. This, I'm really proud of. That's the U.S. regulatory limit for hydrocarbons plus NOx. Anyone will tell you, a lot of companies, they're high-performance vehicles, they do fleet averaging, right? The dirty ones, you know, the high-performance Mustang gets offset by the 4-cylinder, you know, EcoBoost one, and, you know, so the average, that's what the law is. What's a company your average has to go under. And anyone will tell you is a big bore, heavy cam overlap, huge throttle body twin, a very large bore area is going to be horribly dirty. We have 75% margin over what the limit is. But we bias a little more because I think CO is worse. We're over 90% margin over what the requires for CO. We don't do that without engineering. Yeah. and a lot of innovation. This is a shot of the mapping. Mapping inside the ECU is really complex. There's a lot of data coming in, a lot of stuff you have to map, a lot of things that have to talk to each other. We like the ability to write our own software. If you buy from one of the major companies, they only give you a couple knobs to turn, and then they do everything else. So when you want to do something different, like you go, hey, you know what? If we put a little boost port in there and operated a valve with that, we could do that. Like, that's not in the system. That can't be done. So we can do that kind of stuff. So that's the story of the engine. I'm really proud of it. It's a great engine. It's raceable. It's won a lot of races, but it's a great engine. It's a great street engine. It's durable. It's got huge mid-range. You can ride it anywhere. You can ride it fast, but you can also ride it slow. It's not just a race engine. It's a great engine. And that's a few things on the chassis. And I'm not going to go into this in detail, but if you guys want to ask some more questions at the end, I'm going to go through the brake system in detail, just because people always are bugging me about that. We've done a presentation on that. The chassis, we have a term for it that's called OSR, which is optimized stiffness ratio, which is a huge thing, and we worked for decades to develop this. I first started working on this stuff back at Harley in the days of the FXR and the FLT, when they were doing these rubber-mounted bikes that were, the pre-production prototypes were so awful handling, you can't imagine. And obviously we couldn't release them that way, but nobody really knew what to fix. So I started hanging instrumentation on them. Back then we had a 14-channel telemetry thing, which was huge. You put on the back of the bike, and then it could send telemetry back to a truck that we had. The AMF had bought that equipment. Nobody knew really how to use it. But we got that all up and running. And then it would print out strip chart recorders of data. And then I'd sit there with a little, a ruler and measure things and count number of inputs. Didn't have PCs back in 1981. But one of the things I learned was when we were mapping, and I started, and this is also right at the time I was doing the RW750, my Formula One bike, so I started trying to develop that. Okay, what's flex, lateral versus torsional rigidity versus working? What are the things that are key? What are important? The bike's leaned over in the corner, you need to have some flex in it because the suspension can't do everything when the bike's over 45, 50, 55 degrees. So you got to have some flex in the chassis. So how much works and how much doesn't? But what about torsional flex? This is lateral flex. This is torsional, right? So getting the right ratio of that, and also getting damping in it. Because once again, with shock absorber, suspension unit's neat because it's got a spring, but it's also damp. So you've got to somehow build that damping in it. Not just the right spring rate, and not the right, there's also resonant frequency. What frequency is the frequency response going to be at? Is it at something that sets off as something else? So it's really complicated to do. But that's what we try to work on, is find this optimum stiffness and damping ratios for the chassis. And so that frame that has high walls is also pretty thin this way on both sides. And the exact size of that stuff is a lot driven by what we want to get the chassis to perform like. And the other thing is, it's coated with a liner in it, which that's there in case people go, it's a liner in case the aluminum leaks. Well, yeah, except that doesn't happen. Steel tanks and aluminum tanks don't leak either. Actually, it's a damper because it kills the frequency. And it's also, aluminum is better than steel because steel rings more. So aluminum is deader. And that's what you want. You don't want to hit a bump in the corner of a flex and then do this, right? You want to go. So that's what we've worked on in the whole swing arm and chassis design. And again, every new model we've made it better. And the EBR is the best thing we've ever done. We also worked on lightweight. If you ever picked up a subframe or a wheel, and I have a wheel here with a brake rotor that you can pick up. I wish I had a competitive one here because you'd be stunned. And I'll talk more about that on the break, but it's pretty interesting. Again, everything is done with FEA optimization. The subframe back there is magnesium. We have a lithium-ion battery, and this is each wheel design. And we've proven it on the racetrack. We've raced with factory tunes. We're the only American company that's ever gotten points in World Superbike, and we would have done a hell of a lot better in World Superbike if we hadn't ended it in 15. But even more important, we've got private tunes winning and getting on the podium all over the world. It's a great bike. The other presentation I have is brake presentation. And those of you who've ridden Buells or HYRs, I've always heard people going, man, he only has one brake on and it can't work. What's he doing? What's he thinking? You know, I just like to be weird. I had an interesting, one of these kind of blog group was sending me a message. They said, well, a guy kind of, sent us a message and he was bitching about your bike and said he had heard this stuff on another blog where some journalists were talking about how stupid your design was and the frame makes no sense at all and all this stuff. And okay, we've been rated best handling bike in the world. So people go, yeah, you want the best handling bike in the world, but this wheel is stupid and this frame's stupid and the swing arm's stupid. Okay, so if I make all that stuff like everyone else, then I'll be by far the best bike in the world. Except, I wonder why that would happen. So, again, this will be a fun presentation. This is one related to one I did to the Csi Global Brake Symposium that got a whole lot of excitement out of people in the brake industry, including the automotive world, who found this extremely interesting. So, I'm going to play this and talk about it. So, this is Isle of Man. The Isle of Man is an insane race. And it's usually run by a handful of absolute madmen. And also it rewards finishing position speed, because that has crazy top speed. But the reason we like to run there is it's on street roads. These roads are crazy. They're slippery, they're bumpery. Watch the wheel. You're seeing it over the bumps and stuff. This is not like any other racetrack in the world. All the other racetracks are. This is like a real road. And it's intriguing, and it's a great test because, that's one place you don't want your front wheel to wash out or something. So here we are. We want to go race some superbike, and we got to want credibility as a brand. How are you going to do that? Every product out there is good, whether it's a Honda-Yamaha or a CBR 1000 or a BMW, and they're all great bikes. So how are you going to compete and win in the environment? You don't have cubic money to get horsepower. We can get pretty damn good horsepower, but horsepower, kind of goes on a dollar curve like this. If you're going to go from 180 to 190, that's in this part. If you want to go 190 to 200, that's in this part. If you want to get to 230, that's somewhere up here. So we try to use the innovation to do things that we can. How can we do something that's out of the box? So what does it mean? Okay, here's a conventional brake disc. Everybody uses it. It's got strengths. Everybody uses it. It's refined. It's been used forever and ever. You can pick up the phone and call 1-800-BREMBO, which does and buy something, right? It's an easy solution, right? The problem is, if you want to get the really good stuff, that's 10,000 euros. The stuff that they're running on the track is not the stuff that's on the Ducati. We bought it to compare it. It's like, woo! Okay, but it's better. But that's what I'm getting. It's the incremental level to get any better. It's been so refined. The cost is going skyrocketing. I've got two other things I hate. Weight. I hate weight on a motorcycle. I always want to build the lightest possible bike I can. And I hate parts. It's got too many parts. I look at that exploded drawing and it makes me sick. Now it's got another thing that we don't talk about much in motorcycle world. The car guys talk about it a lot. Maybe the reason why we don't talk about it much in the motorcycle world is we're really, really bad at it. So for unsprung weight, the idea is your car or your motorcycle riding along and the wheel is going over bumps. That's unsprung weight. Everything that's floating on top of the springs is sprung weight. Now, what winds up happening is when you're going over bumps and the wheel gets kicked up, this weight of this vehicle and springs have got to get the tire back on the front. They've got to control it. Now, a typical performance car has got a 40-to-1 vehicle weight to one front wheel. We have 12. Typical superbike is 12. We're not in. There is no car, not even a performance. There is no car that's as bad as that. So motorcycles have a really hard time controlling the tires. And anybody who races at a high level, front tire chatter, nightmare problem. That's because the tire is trying to do the suspension work. The suspension is not doing it. It can't. We don't have tire chatter. Anyone who races our bike does. It just doesn't exist on a It does not exist. And that's because we worked hard to get the wheels light. So, to go back to the original story, when we were first inventing the inside-out brake, we sat down and we said it has to do all these certain things. We do this as a kind of what we call our engineering process is we go through everything we design that's new. So with a boundary diagram of external factors, things that the company needs, and then components that something's going to attach to. Because I always want to consider them and see if I can unify them or reduce them or shrink them, make sure the effect on them is right. And then make sure that I'm really thinking about everything out there. And quite frankly, I told the guys, break any rule you want except physics, Just stop and say, okay, those are the rules you don't break. Stop it, don't look at what everyone else is doing. But you still have to be engineers, so you have to go back and look at engineering. So this is what we came up with. Most of you guys are aware of this. We have a large diameter single disc inside-out mounts caliper from the inside. And really, it only worked. Well, this is a good shot because this is Mark Miller at the Isle of Man. This is with the BMWs. They were much faster in the straightaway, beat him in the race. But we've got 2 shots of a video that when he was much worse than on a regular racetrack because the road is so shitty. Now this guy had passed him. When you see him come out of the corner, you see a guy pulling away again briefly. Mark loves the bike down for that reason, because it just hugs the road so well. Like I said, it wasn't easy. This is uncharted territory. Nobody does these. You call up the brake companies and say, we want to do this, and they go, you're insane. It'll never work. But we did the analysis. One of the things we did is ask some of the brake guys, okay, we're not brake guys. What are the calculations you use? Start looking at their fundamental calculations. They say, you start with this. If it doesn't break this, it's not going to work. Well, the calculations they use, they don't have anything with air. They don't have anything with airflow. They don't have anything related to velocity. It's all mass and energy. Well, I got to like, now this works. If you're building one of those copper hauling trucks that's going down the hill and it weighs about a quadrillion tons and the brakes are smoldering, because you've got to snot this weight. But we can't make energy unless we're going fast because we're going to weight. So it's MB squared, baby. So if I'm going fast, I got air. So we did our own equations, looking at it in a different way, which is to say, let's use the cooling air mass and look at the whole brake system differently. And as you can see, you can get the brake red hot. There's a lot of energy you can get away from it. You get cool air on it. Every race car, you see this happening too. I don't see very many bikes do that because they're foolish, because they ought to take advantage of the weight they could get rid of. But you've got to change other things like the car guys have done to do that. So we have an air scoop, we changed all the mounts. The disc has fins going inside and outside about that long if you look at it. It's split in fin to get more surface area in an area where it doesn't have to absorb heat. We did FEA work and CFD work on everything on the system. The caliper, the airflow around the wheel, the airflow, what's happened on the mechanical loads, what's the heat transfer through the mounts. And did a ton of work there. We also found the right alloys that would work and the right pad materials that would work. And at the very highest level, it gets picky between riders, but that's at the very, very fine edge. So it's easy to pick a brake that will work for almost everybody. If you get Danny Eslick versus Jeff, they might want something slightly different. We've done 3 iterations on the brake caliper. It's pretty damn good now. There is more to come because it's not mature. Nobody's done this before. We're still the only guys doing it. So we have a 4th version that we've done that drops the temperatures 150 degrees C. Wow. I just don't have the money to do it yet, to tool it and stuff like that. And as it is, it's a hell of a brake, as you saw before. And I got another iteration of it. And again, the cooling, one of the things you find out is, they go, what's that stupid looking scoop doing on there? Well, that stupid looking scoop is actually catching the air that if you go CFD, that air hits the front tire and goes around. It never goes into the brake disc for anybody. So they got to have a ton of mass to absorb shit because we're not getting any cooling from the airflow. So we capture that air, we go outside of the airstream, like you see in this top corner one, and catch fresh air, and then ram that right into the caliper and feed it through the caliper onto the disc and the pads, right where the so where you get the max delta T, you get the most heat transfer where the delta T, that's difference in temperature, the one spot in there, so the maximum difference in temperature is the maximum BTU transfer rate. Get back to the weight reduction, what we were looking at originally, which was our goal. So we got a brake that works by doing a lot of work, but the big thing we were after was weight reduction. And typically, against typical competitor brakes, you're talking about a 7-pound reduction, because you're not talking about the wheel and the disc, you're talking about the bolts that hold it on. You're talking about 2 calipers instead of 1, you're talking about bolts that hold the caliper on. And you're not only talking about the fasteners that hold the rotor to the rotor carrier. Oh yeah, you have a carrier, right? You've also got the bolts that go to the carrier and then the ones that go to the rotor. So, and then you've got brake hoses, 2 of them, filled with fluid. And half of that weight is on spring. So what we're able to do is bring an incredibly light wheel. Now, is a MotoGP wheel maybe as light as this? Probably. It probably costs about 10,000 euros. This is on a 10,000 euro bike. And we get an inertia reduction, which is another thing I wanted to talk about, because people go, well, that big rotor on there, it's going to increase the wheel inertia, and it won't turn. And I've had journalists break that up. I'm not sure. I talked to my friends at Yamaha that live next door to the hotel Boulevard, and they told me they can't work. Okay, yes, we have a bigger rotor. Yeah, 386 millimeters instead of 336, which is a typical dual system, right? That's a lot. And inertia squared with the diameter, so it's not only bigger, you've got to square that difference. So if you do that, the EBR rotor has 1.36 times the rotational inertia of one of the competitor's discs. But they have 2. 2 times 1 is bigger than 1.36. Oh, and nobody counted the carriers. They're rotating. And nobody counts the spokes in the wheels, which have to resist torsional twisting, because if you grab the rotor here and go down through the hub and then back out to the tire, those things are torn each other apart. It's just like trying to turn a bolt and a nut, right? That's what it is. We have much less inertia. That's why the bike feels so light, handles so well, is so stable. And then back to basic engineering stuff. I mean, we have, I don't know what's on here, but if Boothroyd and Dewhurst, they have all these formulas that you can do if your grapple is complex, and there's by number of inches of machined area and number of fastener holes and everything. You don't have to do that. You just have to look at it and go, dear God. And this can be broken down more than this, because I haven't broken down how many O-rings are in the pistons, or this is just a big high level look at it. You got 47 to 12 items. What in the world are they doing? And there's another thing that boils into it, which is quality. One thing that you want to be able to do, have a really good way to work with brake, is you want to have the caliper pretty centered on the brake rotor, close to centered as possible. Okay, if you have a standard dual system, I've got a wheel that's going to be machined in a lathe. I'm going to machine one side of the lathe. Well, I'm going to have to take it off and change the setup, unless some crazy machining center that holds it by the rim and can machine both sides at the time, which I've never seen. Okay, you got a tolerance stack up, because to make those two exactly the same width, it's going to be hard. It's going to be expensive. So I've got to get both of those centered. Okay, now I'm going to mount it on the fork. Okay, somehow I've got to register the wheel bearings against one side of the fork or the other. Well, okay, then that's never going to be completely the same, because they're the triple clamps and they're castings and they're machined. You start running through the stack up of tolerances, it's crazy. And it's what led them to radial brake calipers. There is no advantage to those other than the fact that instead, you bolt right to a face, it's going to lock in the location. So guys who are racing have to shim them. With a radial, you can drop them in place, have just spacer shims and tight bolts. It's got float, so you can center them right away. I don't have to do that, because I machine the fork leg that the brake caliper mounts to. It gets machined on one side for what sets against the bearing. At the same setup, it also machines where the caliper mounts. The bearing bore gets put in the same time as I machine a ring of mounting things for my disc. I'm done. That's my total stack up of tolerances. I love this one. And you know, this is seen on TV, but when you hear people go, you know, that brake system doesn't work. Watch Danny and see what Scott Russell thought. So this is Danny Eastlak back in when we were running the EBR, an AMA Superbike at Homestead. Most of this is him racing against Blake Young, a hell of a rider. Finished #2 in the championship several years in a row on Yoshi Suzuki. That Suzuki has full works Brembo system, radial trick, old Superbike system on it. You can go look pictures of it online. It's how cool it was, trick was, a beautiful bikes. Danny's running a stock brake system. Actually, not quite as good as what's on here because we've evolved since then. So.
Okay.
Rest my case, man. We're not as fast as the other guys. We don't have money running a team, but our ideas aren't stupid. They're pretty cool. It's real engineering behind it, and you know, like I said, for us, we're running the same thing we're selling on the racetrack. It works. The advantage is even bigger on the street. That's where it really matters, because that's what I want to build this for. I want to race to prove it to brand. I really want to build a great street motorcycle. And on rough and bumpy roads, it's just so nice to have a front end stick always, you know, and be able to brake sooner, you know, because as soon as that front wheel, the heavy front wheel hits a little bit of stutter bumps or anything like a roughness coming in the corner, as soon as it goes into, I'm sorry if I'm not loud enough, the dynamic coefficient of friction, you know, as soon as the tire slides, you've got to get out of it to regain traction again. So the longer you can hold that off, the shorter your stopping distances are. We have really short stopping distances at rough, which is the stuff you run into. And so we fight hard for it, and I really appreciate it. And we also won every race in 2015, so it's in China, only bike on the podium with production brakes. I'm the only one that has the ETL. And so, thanks for letting me talk about this stuff, and I'm willing to talk about anything technical. I really appreciate it. I can't thank you guys enough for coming out.
Eric, I'm going to start out. Some of you people rode demo foot today, and you've all heard this sound of deacceleration. Can you explain to us up there what that sound is?
Yeah, we can talk about
Why do you do that?
This is, the sound you're hearing is this system here. One of the things that we shot for, and again, maybe, you know, we're really trying to make a very rideable superbike for the street. But one of the things that I always wanted to be able to have is, that, you know, when you have chain slack and you get on off the throttle, which happens, everybody wants to be perfect, but you don't. And you drift and you get off the throttle and you get back on it again. There's chain slack in every system. And when we were doing the Buells with the belt drive, one of the things we had to develop was that belts have to stay in constant tension, especially with a lot of horsepower through them. Belts get loose at all, they tear the teeth off, they chatter. So one of the things we realized was, when we did the math, we were able to find a spot for a different axle location where you could actually maintain almost perfect tension. Now, if you don't have that, where these three go in line is going to be the tightest spot. Okay, that's the longest difference where this sprocket is and this pivot point is in the axle. Straight line for them is going to be the longest distance between these 2 points, right? So anywhere you're not in that, you're going to have looseness in the chain. That's what this is put in there for, so that we can keep the chain tension tight. So one of the things that you have to do when you own an EBR is you really need to keep the chain tight, much tighter than people think, because people are used to adjusting and knowing that you're going to hit this spot. And if you don't adjust them with a bunch of slack in them, you'll ruin your bearings and you know, you'd be pulling almost through an infinite stiffness. You're trying to force this chain over a distance it can't reach. That's why we did it. It's weird. It costs more money to put this on than not have it. And it's one of the things that makes the bike just feel like it's one part of you, you know, so that, you know, everything you do, it's connected. There's no gaps, there's no hesitation, there's no wobbles, there's no chatter in the front end, there's no any of this. I'm trying to make it just feel like when you think it, it's going to do it.
So, Eric, when you mentioned it though, but when you adjust the chain, I mean, basically you just adjust the chain tight when it's on the side stand, right? Can you just
Yep.
explain that?
Yep.
Make sure
Yeah.
everything's
Again, it's a typical thing is people are used to adjust. I mean, most people don't want to go and, you know, when the bike has a shock absorber on it and stuff, you can't get it into this position when they're in line. So people compensate for it. Most good mechanics are used to saying, oh, wow, I got to put some slop in this chain. It's too tight. You don't do that on this bike. You got to keep it snug.
Yeah, because if you leave a drop in the chain or put your normal 20 millimeters slack in your chain, you'll ruin a lot of parts in this motorcycle.
Yeah, well, what happens is it just, you know, then it's just flopping around all the time because it never even has a tight point.
How much weight did you lose being with your chain? How much weight did you lose when the chain developed?
I would say that we added weight when the chain developed. Actually, I'd be willing to bet. I've never made it weighted. So there's a couple of reasons. Biggest reason for going with chain was it's a super light. People want to change gearing. You can't do that with belts. It's a nightmare. I mean, the sprockets are crazy expensive to tool. You can't really billet machine them. You can't. It's really hard to get one right because the tooth profiles are really weird. But you have to have a different length belt for every, you know. So it's just not like a chain. It's a lot more convenient to be able to do this. A clean chain is actually slightly more efficient than the belt. As soon as it's dirty, it's not. But again, on a racetrack, people put clean, make sure it's fresh. As soon as it gets dirt and stuff in between the plates and they start grinding, then it starts burning up horsepower more. But it's, again, you got 185, you got a little bit of spare, it's not going to be a lot. But if you're getting down to the engineering facts, that's the way it is. But that's why we did it on the bike, is so you can be able to change gearing.
So with your chain system, with this, correct me calling it just an idler, when the chain wears, as chains do, they get that tight spot.
Yeah, you have to adjust to the chain, but the range that you adjust for chain is such a small amount of this that it doesn't affect it in a really measurable way. With the belts, we had a fixed axle location on the wheels with belts, so literally we're always in the same place. But you know, if your chain gets loose, yes, you have to readjust it, make it tight.
Right, but I mean, like in the chain's life, how at a certain rotation where it bends in with the sprockets, there will be a tighter spot in its rotation.
Yeah, so it's not completely bowstring tight. It has some play in it, but it's way, way less than people are used to seeing.
Right.
So who's gonna go home and start designing a motorcycle?
Hey, Eric, the expert. Explain what that big gold thing is that ties the countershaft sprocket.
This?
Yeah.
This is another thing that he did that's different. It costs a whole lot more money. Again, trying to get unsprung weight down on the rear, which is harder because if I'm out of the sprocket from the outside, maybe I could get some weight, but I'm putting torsional loads to the rear wheel. I was able to take a whole lot of the hump weight out of it. If you look in here, you can see the spacer in here, right through it, so I only have a minimal amount, so I got a good bit of weight out. A push drive system adds all the weight of the push drive system goes on the wheel, so it's 100% unsprung weight. So we put it here. It doesn't matter which end it's on. So the idea is to make a sharp jerk on the rear wheel, not smack the engine, have some sort of give in it. So we just put the give on this side, which is fine.
Full of rubber?
Huh?
That's
Yes.
just full of rubber?
Yes.
And it's just the opposite way that the sprocket goes in the hub.
But that's what it was done for unsprung weight, and it's not the cheapest way to do it, that's for sure. And you got to design everything yourself again. Eric, you got a question over here?
You said that your brake pads last longer or shorter or about the same as the traditional dual capital setup?
Well, it would depend on the pad choice and the situation.
On average, I won't hold you to it.
For normal street riding, I guess there's probably guys here at home using EBRs. Durability's fine. On a racetrack, I think they wear a little quicker than the dual systems. But our 4th gen caliper, they won't. So the 150, that'll be there. But, you know, can you get through races through them? Yep. There's the Isle of Man and everything else, but it's a little higher wear, but that seems to happen when they're really, really, really hot. So on the street, the wear seems to be identical to the system.
Quick question, the 1125 was that a Rotax, that was a Rotax motor, right? Was that made by Rotax?
Here's the deal on motor. We wanted to do a motor, and we had parameters of what I wanted to do. I could design the original VR concept engine, and then it got taken away. And then I did the V-Rod engine, was going to be a fuel engine, and we started it with Porsche, and then Harley said, no, it should be a cruiser engine. And so they got that engine, so it was my 3rd run of that engine. So I knew what I wanted to build. I didn't want to buy a Rotax engine, but Harley was busy with other engines, and so they said, you've got to find someone else to work with you to design the engine. And then once we finished the engine, they said, well, we don't want you to building engines in your farm, because engine assembly is a Harley in the U.S. So, and we don't have the capacity to build it, so they're going to have to assemble it for you. So they had a unique line there that was separate from all their other lines when they put it together. But it's a unique engine. It doesn't share components with any of their other engines. And so it was sort of
who makes the engine now?
We do.
So you do all the tooling,
100%. Yeah. Rotax doesn't make any parts for it, so all the pieces, they don't even, not only do they not assemble it, they don't actually make any parts. But because it was such an odd engine, they were buying all the parts on the outside anyhow, except for 3 parts. Those are the only ones they were making. So we just had to find, so we went back to most of the same suppliers they were using for that stuff, changed a few, and then we had to find new suppliers for the 3 things that they were having.
And how does the engine differ, this engine now, from before the receivership to after the receivership? I've talked to some guys, they said it's doing a little better, this, that. I mean, is it the same?
The fundamental engine, the EBR 1190 RX and SX engine is the same for before and after the receivership. The calibration is different, so it's been tuned, it's got a different tune in it, which could be downloaded into the other ones. So we did about 6 or 7 refinements, but it's basically the same.
If I could add some evidence for my ownership of the 1125R, in 63,000 miles, I changed my front patch 3 times. I have everything I ever done.
You got a good record like that. Wow. From yours.
I'm glad to share them with you.
Yes.
You mentioned that you used optical scanning to scan competitors' fights.
Yeah.
As well, you mentioned that you were using strain gauges to measure torsional load, lateral load on your frames. Have you used optical technologies on your frames to measure strain? Now, I'm asking because at work I'm using Dome software, which is 2 cameras or sort of a random pattern paint put on it. You put your wing spot through some strain, and you're able to get a color plot and measure microstrain across the whole rather than pinpointed parts.
That's interesting. I'm wondering, probably pretty expensive equipment. What we do is, we'll put strain gauges, a pattern of them all around the frame, and then run it through, like we'll take it to a racetrack and have a top rider ride it hard to make sure that what we're getting the loads right. Then what we do is come back and duplicate that in the lab. So put it in our testing and puts hydraulic loads on it, and then get it to match up. Now we've got a load that we can put in a computer simulation, and we can see the deflection of the frame and the hotspots and that kind of stuff. What you're talking about is pretty interesting. If you could do that then on live post processes, that's something that might be of real value for them to do, especially if they're making carbon. It almost might be a quality inspection tool for them to use, because with carbon, that's kind of strange stuff. You want it to be right. And so how do you check it? That would be a cool way, because you could always check and make sure the deflection was as planned. And if it wasn't, that means something's wrong in the matrix, layout or something. Pretty cool. It's cool. The stuff that's going on in, modern technology is just really, really fun tools. I'm always looking for more. Some of them are unaffordable, but if we can get them, they're great.
So I've always seen it on one bike previously. It was the BMW. They had a 450 dirt bike.
With the pivoting on the
yeah, where the swing arm pivot and the transmission output shaft are shared. So
that's a nice thing for chain tension, but it's a really bad thing for chassis geometry because you can't get any squat out of it.
Right. Okay. Yeah.
Which is a really
because then you don't have to plan for any changing distance in traffic.
Yeah.
But so that's the issue. You can't.
Yes.
Okay.
Actually, where you have the swing arm pivot and where the engine sprocket is and all that stuff is a geometry that really makes a difference. So you want to have anti-squat in it, so when you're accelerating out of the corner, it plants the tire instead of lifting the tire. So if you have with concentric, but like Sportster, for example, they've got this swing arm pivot really low, and it goes over center like this, and it actually drives the bike. The chain actually lifts the tire off the ground. Kind of cool and flat. It doesn't work so good for traction on pavement.
So off-road, that's what happens.
Yes.
So with the change from the 1125 CR, the intake, I see on the SX a lot smaller and it's also lower. What was the thinking behind that?
What's smaller and lower?
The intake. So where the fans and whatnot sit?
For the radiators?
Yeah.
Yeah. Well, it's just a different radiator lab. We have on the 11 experience. So I really based it off of Porsche, who I have huge admiration for. Porsche is a really cool company because they have Porsche cars and they have Porsche engineering services. And when we work with Harley, we work with various consulting companies. Like I said, Ricardo and ABM. By far, the favorite was Porsche. And the reason is because they make cars too. So the ABL guys tend to be la la land. It's like doctorates and blah, blah, blah. And it may not be what they come up with, may not be producible. Right? It's a cool idea. But Porsche guys, because they live in that world, and they do that swirl. They take Porsche guys and they put them in engineering services, and then they move them out to the cars, and they move them through there. And they're really good. Plus, then their engineers get to work on different stuff, and that's fun. It's interesting for them, keeps them from being jaded, So they'd be working on a motor for Mercury Marine, or they'd be working on something, And so that's kind of the model for that.
Got a question. Not asking you to look in the rearview mirror, but for us fuel guys that are still kind of loyal to the old Harley engines, is there going to be any sort of possibility that EBR ever starts? Now that Harley, does Harley still own the parts, or can you start making?
Harley owns everything. They won't let go.
I
call them. I give them my annual phone call.
They even own the guy's name.
Very good.
It's not
sorry, man.
Just look forward.
All I can do.
Guys probably talking to me on the phone or parts of EBR, that's me. I'm sorry, I have to break that email. We cannot get you the fuel parts. It's sad. And we all in the office kind of, Eric may say, we sit there and how can we help you guys? We really do.
You can build badass bikes like this.
Well, that's
what we did.
We got a beautiful bike coming off the line. We own the bike. Harley won't mess with us again. So there's your opportunity.
Turn in your fuel for a remake of an EBR.
Sorry, I didn't hear. What was that?
Upgrade plan.
Turn in your fuel for a remake on an EBR.
Well, you have to talk to the dealer.
One more question, if you don't mind. Is there any chance in the future of a single Tesla drive type motor going into an EBR bike?
Electric?
Electric bike? Yeah, an electric bike, but with, modeled off something like what the Tesla has done.
That, I talked about that a little before, and I did a little thing before I did this, and you might not have been there, but I worked a lot on electric stuff, and I was trying to push it inside Harley when I was there as part of Buell, and I wrote every brand that was out there, and Harley went to talk all those companies about maybe buying them and blah, blah, blah. The issue with a regular motorcycle is, you know, there's still a struggle in getting enough range in a powerful vehicle at a reasonable weight. It's just not really there. I'm not sure how quick it's coming. It's coming slower than the proponents are going, but a little faster than some of the naysayers were doing, and there's a lot of money being thrown at it. What I like, and what we did at EBR as a consulting project, was a serial hybrid.
Yeah, the scooter.
And that, man, that just takes a lot of money to do. I would do that. That's very rational, you know. So if you build a hybrid that had a battery pack, that you didn't have to carry the, you know, because I used to run them, I don't know the top of my head, you know, but you know, if you wanted 1,500 kilowatt hours, it's in this much gasoline, it's a gallon, right? And it's this much battery.
Yeah.
So the thing is, use the gasoline wisely. And the serial hybrid thing that we did, we built an engine that was super efficient. So that's the bad thing is, fuel is actually a wonderful storage medium. Gasoline is incredible amount of BTUs in an incredibly small space, and actually it's known how to be handled well, you know, all the process, everything in place. The problem is the engine's just wasted. Now there's progress going, but when I could do this deal, what we did with serial hybrid, again, for those of you who weren't here, was serial hybrid is the vehicle is like a Bolt as opposed to a Prius. A Prius is a parallel hybrid. The gasoline engine and the electric motor both drive the rear wheel, so they have two different control systems and two different transmission systems, and all that has to work together. That's just too heavy and too expensive for a motorcycle. Again, motorcycles have to be cheap and they have to be light and compact. And so what I picked was a serial hybrid, which is like a Volt, which means the gasoline motor just charges the battery. And so when I did that, we designed a new engine, which nobody had done anything like it before. Porsche wound up helping me on it because we went in an incredibly tight window, and in trade for that, I gave them the rights to use it in a car. Whether they'll ever use it there or not, we don't know. But they liked it enough to say we want it. Anyhow, the engine only runs at 1 speed. So all the generator systems that you ever see around, you know, or like a Honda generator, it's a Honda, little 100cc Honda engine that you are starting at idles, and then you rev it up, and then it takes generator. What we did is have a big alternator on it, and then that also was a starter. And so when the battery would get low, this starter would spin the engine up to the running speed of the engine, and only then would the engine start. And so it just had a hole and a fuel injector. There was no throttle body, there was no control. And then the power, you kept it from over revving, you pulled max power out of it just by the alternator system, by how you pulled the power out of it through the control system of that. So it would run, fill the batteries, shut off. The cool thing about that is if you're riding a super bike down the highway at 60 miles an hour, how much horsepower do you think you do?
Very little.
20?
Less. 15, 14. How big of an engine do you need to make 14 or 15 horsepower to keep your headlights on?
Very small.
Very small. And if it only ran at 1 speed, it can be damned efficient. That motor that we had, that serial hybrid, was over 300. I think it was 340 something EMPG. So if you had a little 250 motor like that, 1 speed 250 motor that could zoom you around at 60 miles, and then you had this 250 horsepower electric traction motor that when you open the pipeline to the batteries would go and bury people, man, you could ride that a long way.
That's like the.
And you wouldn't have to have 400 pounds of batteries or something like that.
The
Anyhow, that's just me.
Right.
I could do a lot of things with money. Like lose it all. That's my wife. She'd be throwing things at me right now.
Eric, is a lightning going to be at the bike show?
Yes.
What are the difference? Can you talk about the difference between the lightning and the SX?
We can, but we'll have to be up after.
It's come down and see it. It's cool.
Right.
It's nothing rad. I hear people posting online. It's going to be a chopper.
You gonna be part of the test drive?
Not at all. No. It's just
No test drive?
different, nothing derivative. It's got 185 horsepower. So. Huh?
Come see us on Friday.
No, yeah, right. Guys, let's give Eric a